Okay, so this talks about ABBE, a new solution, new approach, and also a new tool to detect attacks in Ethereum smart contract. Okay.
Hello. So, hi. Hello, I'm Bao. I'm currently a security engineer at the VN3 Corporation with a company in the Vietnam. And I'm also a CTF player. I am currently the leader of this team. And this CTF team is the CTF team of the University of Technology at Ho Chi Minh City. Welcome, you guys.
Okay. So my name is Nguyen Quoc. I'm working in Nanyang Technological University in Singapore. So actually our team has few more researchers, but sorry they're not here today. Okay, so this talk we take a quick look at the background of Ethereum smart contracts, Ethereum platforms, and we try to classify the vulnerabilities that can happen in smart contract on Ethereum platforms. And later we introduce our own solution named ABBE. So you can see how we can detect that attacks and how we build and design the ABBE solution and tools. And after that, we show you the result, how you can use our solution to detect attacks on the Ethereum blockchains. And we have some live demo as well. Okay, first part, some background on Ethereum smart contract. So the idea behind blockchain is very simple. It's public distributed database that all the update on the database cannot be reversed. And blockchain has some very unique features. So the platform encourages people to participate into maintaining and running the blockchain. And on return, you get some rewards, which can be a token, like Bitcoin, for example. And Ethereum is another very unique blockchain platforms. It tries to push the idea further by introducing the new concept of running program on top of the platforms, on top of the blockchains. And we call the programs running on Ethereum blockchain smart contracts. Okay, so the idea is you can see on the diagram, we write the smart contract in the source code, and we use some compiler to compile the source code, and you get back the bytecode, and you deploy the bytecode on the blockchain, and the bytecode can be executed upon request. And like any legacy programs running on Ethereum blockchain can be vulnerable and can be exploited. And actually, people want to attack smart contract because they hold some very good economic value inside the contract, because they have some. It can store many Ethereum tokens and also some private tokens. So the idea is simple. You can send some tokens to the smart contract with some request, and the platform will execute the smart contract function for you. And internally, the smart contract can call another smart contract. So smart contract also has some permanent storage. So the idea is that each smart contract can be given some private storage, and smart contract can have some internal state, some internal variables, and the private storage of each smart contract can keep all of those internal state and its internal variables, like you can see on the screen. And the storage of the smart contract on Ethereum is organized into slots. So one variable can be in one or more slots. Okay, so because the smart contract on blockchain can hold some huge money in terms of tokens, a lot of attackers want to attack the smart contract to get the money out. And we show here some very big cases. In that, the attackers can attack the smart contract and get out millions of US dollars. Okay, so the question is how to detect bugs or vulnerabilities or zeros inside smart contract. So far, there's many solutions, but all of them focus on auditing. So given the source code of the smart contract or the bytecode of the smart contract, they try to audit to find bugs inside smart contract. This all happened before we deploy the smart contract to the platform. So in this work, we try to have another solution, another approach. So we do not audit the code, we do not audit the smart contract, but we try to monitor the smart contract when it runs on the platforms. And by looking at the transaction happen when on those smart contract running, you can try to find something abnormal. And based on that, you can detect attacks. So here's the idea. We look at some smart contract running on the blockchains, and we watch all the transactions happen with the smart contract. And based on some known patterns of vulnerabilities, we try to find the abnormal behaviors happen with this smart contract. And we can report if something wrong happened. And based on that, we can also detect zero-day attacks happen with this smart contract. Okay, in the next part, we look at some known vulnerabilities happen with smart contracts. Sorry, okay, yes. So the bugs happen with smart contract can happen at many levels. First one is programming language level. And the second type of, the second level is bytecode or virtual machine or even compiler level. And then some bugs can also happen at lower level of the platforms, but that's out of scope. So in this work, we focus on detecting bugs happen in the programming language level and bytecode or virtual machine or compiler levels. Okay, so first type bugs happen in the programming language level is called reagencies, which is very famous case happened a few years ago. The idea is that the contract can hold is a token, right? And the contract can clone another contract. The problem happened here because you can see that when the contract clone another contract, it can execute the fallback function. And if some logic is implemented wrongly in the smart contract, it can update the state before it sends the money. So you can see here on the screen, the attacker. Okay, so we have some bugs inside the withdraw function here. So you see that this function tries to check the balance of the sender. If the balance is more than the money he wants to withdraw, it sends the money back to the attacker, right? And only after that it updates the balance. But the point is that the clone function can actually has a side effect. It can clone the fallback function here, and the fallback function here, it can clone this withdraw function again. So here's the reagency issue happen. So you see here that because the attacker can clone the withdraw function again, and here it come back here again, right? And the smart contract checks the balance again. Because the balance is not updated yet, it executes the next function without any issue. And this one will send money again, second time. And because of this, you can see that, okay, the first time, the second time. So the withdraw function is executed 2 times without updating the balance of the senders. And because of that, we update the credits of the balance of the sender 2 times, and at the second time, we deduce the money, and the balance of the attacker become the FFFF, which is the maximum amount of the money the balance can keep. And only after that, the money is deduced from the smart contract. So as a result, you can see that the attacker get all the money inside the smart contract. Second type of vulnerabilities in the smart contract is integer overflow, which happen with own cap probabilities, not only the smart contract. So you can see that here what happened. So the transfer function try to check the balance of the attacker. If the balance is more than the value he want to withdraw, it sends the money to it deduces the money from the smart contract, and only after that, it sends the money to the attacker. But the point is that value plus fee can overflow to be 0. So in this case, you can see that we deduct money 0 from the smart contract, but it sends a big money to the attackers. The next issue is array overflow. So you can see that in this case, because the array, the set function can set the value to some slot in the array, but it extends the boundary of the array without checking the boundary. And what happens is that you can call this function many times, and eventually it overflows the unbounded array, and it wrap back. And because there's some bug in the compiler, it can override to another slot, which is the owner in this case. And you can see that if you call the set function many times, you can override the owner, which is the arrest of the smart contract. After that, you can do something that is not supposed to do. So the next issue is uninitialized storage pointer. So the idea here is that in this function, the donate function, this variable is not initialized, right? And after that, because the way you declare this variable, this one stays in the storage of the smart contract. And in the next 2 lines, you write to the internal state of this variable. And because of some bug in the compiler, this line write to the first slot, and this line write to the second slot, which is supposed not happen. And this line actually, you can see that here you override the owner variable of the smart contract. And because after this, you call the donate function, you become the owner of the smart contract. You can withdraw money, you can do something to drain the money of the smart contract. The last case, delegate call. This one is a low-level function you can use to call function in another smart contract. So you can see that contract A can call function in the contract B. And here the contract B is function as the library, the callee, right? And the idea is that when this happens, the execution of the function in contract B is executed in the context of the contract A. And also here's something wrong with the compiler. Instead of write to the internal state of contract B, it write to the internal state of contract A. So this bug, when you call the function in contract B, you might override some internal state of the contract A. Okay, so that's the part about the background and the vulnerabilities in the smart contract. And next part, we introduce our solution, how we can detect attacks happen in real time in smart contract in the platforms, and how we can detect zero day as well.
Hello. So, yeah. So, in the very first idea, we describe the architecture for our tool as follows. First, since we need to classify all transactions that are sent to the Ethereum network as attacking or benign, we set up a blockchain provider that is set up by the Go Ethereum client to retrieve all the blocks that have been mined. After that, we pause. After that, give me a second. Here. After that, we pause on the block inside this. We pause all transactions that inside this block to retrieve all transactions that are pocketed inside this block. And we also need the identity of the contract that we are observing. So the address and the source code of this contract is provided by the user. And sometimes the source code is verified in the Etherscan, so our tool can grab the source code in the Etherscan without the help of the users. And all of the information about the source code and the address of the contract, and along with the transactions that we have get from the get client, we pass it into a diagnosis model. And from this one, for each kind of attack that we will present some laser, and we will present laser, and the abnormal behaviors will be recorded and reported to the users after that. So how do we extend the architecture to capture the attacks? And I will explain it into some cases that I have proposed. So in the efficiency case, there's a lot of internal transactions that have been created because the characteristic of this vulnerability is that a contract A can call to the contract B, and the contract B is called back to the contract A again. And this attack can internally call to the contract again and again for multiple times. And because of that trace that have been recorded in the transactions, we can use it to detect if there are any duplicated contracts that have been called at least twice. And if there's a contract that have been called twice, we call it like a recency attack have been exploited. So about the integer overflow, all executions in the EVM bytecode are performed and affect to the stack state. For each step of the instructions, the stack state change and leave some interest evidence. In this example, a add operator is executed with two intended parameters, which then cause an integer overflow. Since the size of an element in the stack is just bounded into 32 bytes, so after execute this operator, the add operator give us an integer overflow value. But internally in EVM, there can exist some operations resulting in overflow value. It's due to the nature of the Ethereum, it's not a exploitation. So it will see all overflow cases are the attacks. So this can lead to a high false positive in the final result. To address this problem, we will track along the state of the stack to determine the overflow value originated from a user input. If it's not originated from a user input, so it's not a integer overflow exploitation. And our tool will mark it as a negative case. So years ago, a contributor in the Ethereum project listed all possible cases that can lead to a integer overflow. And thanks to this list, we implement a detection that catches on arithmetic instructions that violate these conditions. About the array overflow attack, it's the same thing with the integer overflow. And the array overflow does have a add operator in here to find out which slot will be stored in the next step. And this add operator will may be offloaded, but the parameter here, if it's the originated from a user input, so it will be a array overflow attack. I'm sorry. So in the previous attack, we introduced the method that perform travel through stack trace and grab the overflow value exists during the transaction execution. Note that besides the transaction information, which includes the data of the sender address, the receiver address, and the amount of the transferring money, the transaction data to trigger the smart contract functions, we also need to re-execute the transaction in order to obtain the stack state history. And to obtain these re-executions, we don't need to have to build a emulator, but we can use the Go Ethereum client to get an API that allows the users to query the debug logs, which is the stack state history that we're discussing. We will use the input of the transactions hash to call this debug trace transaction ABI and pass this information to the diagnosis module and perform the diagnosis process for each kind of attacks. About the other cases, we need some other method to detect. In the get back to the delegate call vulnerability. These vulnerabilities seem to be hard to be detected, since the only evidence that left is the contract storage is intentionally overridden. So we can apply a heuristic that to tackle this problem. If the storage overridden occurs, there can be a mismatch between the type of the variable and the type of the new value. This is because all new data that is pushed into the ether in the EVM storage is formed under a slot which is 32 bytes long, and this new data can obviously not type text in the EVM. So, taking advantages of this trick, we can detect some abnormal assigning in the contract storage. And moreover, heuristic and some variable names holding a particular meaning. For example, a variable name can be a owner or something that is very important. And these variables must not be changed. So if they are changing in the owner value, we can also report a warning into the system. So how do we recognize the mismatch between the variables and the new value despite the EVM doesn't define type in the EVM level? We introduced a model with take responsibility to create a table that maps the variable, the slot index, and the type of the slot. Since we have the source code here, which represent the name and the type of the variable, we can also use the source code to determine each arbitrary variable is stored at which slot. For example, the v-string variable here is declared at the first. It declared first, so it's moving in the slot 0. Since we got the variable name, variable slot, and variable type, we totally can determine this slot 0 must contains a string value. As for the rest, the next slots are also determined by the same rule. The layout of this state variable is in the storage of Ethereum smart contract is well documented in the Solidity documentation. So after that, we got the type of each slot. Each new modifications on the smart contract store is performed by a S store of code, and the S store of code must be checked by our tool because the type of the declared variable and the new value are brought into comparison. And if there are mismatch between the type of the variable and the type of the value in the slot, there must be a overridden that does intentionally. So, since this approach is heuristic and it just not depends too much on the nature of the vulnerabilities, it may use to detect the zero attack in the future. So, the architecture of our tool contains a new model that does the mapping, and we call it the storage recreator. This new model needs the input including the source code, the current value of some specific slot in storage. Some of these are obtained via some APIs provided by the Web3 library. And this is the final architecture of the ABBE tool. So to summarize, the final information that the ABBE tool needs is comprised of the contract source code, the contract address, the contract deploy address, and the storage of the contract can get from the Web3 library. And we also need the transactions that were re-executed as well. So far, with this architecture of the ABBE tool, the attack vector list that we have discussed in the previous sessions, we cite inside the table of the track that can be used for detecting the attack regarding to the behavior of each one. In this table, the impedance that used for the investigations includes the result of each transactions. As for the regency case, the exploiting transaction calls some specific functions multiple times, so it might be leading to a high amount of gas is consumed. So this high amount of gas could be an attack in the final result to detect the attack. So we can use the internal result and the info of the transaction of the regency to mark it as a trace that will be used to detect the attack. So as for some attack vector in the EVM level, including the array, overflow, the delegate call, which are all related to this storage overriding phenomenon, which needs the help of the storage. And this storage is now investigated by the new value that is written into, and maybe the meaning of the variable name. Recall that each attack can be performed by either by a normal transaction which comes from a normal user, or by an internal transaction which is sent from another contract. So the reasons that we have to list it out here is because the data concourse of the normal transactions can easily retrieve from a arbitrary blockchain node, while the information of the internal transactions is get from nowhere, but from the re-executions of the root normal transaction. I'm sorry. In this table, we summarize the input that need to detect each kind of attack vector time. Some attack is currently left blank because we didn't find any reasonable mechanism to detect it. This table is quite self-explanatory. However, the only thing that we have to focus in the transaction column. The transaction column. In the transaction column, the current means our tool can easily detect the attack with a single transaction only. On the other hand, the all transaction mean ABBE needs to re-execute all transactions from the very first transaction that appear in the Ethereum network to the newer transaction in order to detect this corresponding attack vector. So, come to the demo part. The DAO attack. I'm sorry. I'm sorry. Không, em muốn để cái tab của em đó. Oh, I found it. Yeah. Okay, so we have a contract that represents the reentrancy case. Because the reentrancy case requires a timer that needs to execute at a specific amount of time, so we just don't have time to wait for it in the demo part. So I try to demonstrate it in a simpler version of reentrancy attack. So in the reentrancy attack, we have a deposit functions and a draw functions that allow user to deposit her money and draw it back later. So the first step we have to deploy. We have to deploy the transaction. Okay, this screen of auto. So after we deploy this transaction, we have to put the address of this transaction into auto. Okay, so we're gonna put the address of this transaction that we the address of the contract that we will observing. Oh shit. Okay, we put the address of the tool, and then we put the we put the part of the source code inside. So it's also going to load this contract into here and then perform some detections. But it's just the block that previously mined in the network. So now we're going to perform some attack into this contract. The first thing I have to and I will deploy a contract that have initially 10 way, for example. And then, I'm sorry, this regency attack, regency contract is not initialize an amount of money, so I have to deploy it again. It's got about 100 way here. Okay. After deploying, we will put it into auto again. Okay. So now we're gonna deposit the amount of money into the regency contract. So we gonna put the address of the contract here and amount of money. Previously we initialized it about 10 way and we put it in here. Okay, actually executed successfully, and we will check it, the balance of this address. We had 10. So intentionally this contract regency attack will just able to withdraw just 10 way from the contracts in the below, but because of the regency attack, we can withdraw all of this fund by the attack function. The attack function is just like it called the draw function from the contract here, and then continuously call the regency function multiple times. We are gonna do the attack. Which is so after call, the user balance is now succeed a lot of money, but where my regency? But Autumn can find a galaxies inside during the execution of the transaction. The galaxies is one of the nature that the regency attack will give out. So that's what Autumn does to detect the regency attack. For the next demo, we have the beauty chain backed token that is a integer overflow. That exploit the integer overflow. Integer overflow, and in the last year, all tokens of this contract are lost due to a integer overflow bug. So we're going to put in here. The back token is just a contract that represents the token of the beauty chain. In this contract, we have a function named path transfer. This path transfer is developed to send money to a lot of accounts at a time. So in this contract, at this line, the multiplications between the value that have to be sent for each account times the number of accounts that have to receive the money, it will be exceed a integer overflow. So we're gonna deploy the back token. We can apply the A token, and we will see the address, the balance of the owner. He will have a lot of money, and we will act as a hacker that have no money at all, but still able to perform to gain a lot of token inside here. And this the account of the hacker have no token at all. So this hacker will call the path transfer function. Will call the path transfer function with to send money to himself with the amount of 2 of this thing. So we're gonna transact that. Oh, I'm sorry. I forgot to open the observation for this contract. I put it in here. Okay, so what's that? Okay, we will start to observe the contract from the block 216. Oh, what's happened here? I don't know. Maybe due to the network, so I'm gonna play the video of the demo instead. Okay. Here. We first deploy the contract of back token. And then after the previous step that I have done before, and we show that the hacker account have no money at all, and we will put the contract inside our tool in order to observation if there any abnormal behavior. And then after that, we will call the proper payload to the path transfer function, and this is the step that calculating the payload. And after that, we call the path transfer function, and we say that the hacker account have a lot of money. And get back to our tool, we say that the integer overflow has been recorded inside the ABBE tool with the corresponding of code a multiplication, and at the execution step a 165. Okay. And the last case is because we just running out of time, so I will gonna skip the demo part of the Parity wallet. So yeah. So our tool have been tested from many test suites, and the test cases that we have we collect from the attacked contracts and some simple contracts that contain vulnerability that we self-writing it to demonstrate the vulnerability in the contract, and we then try to exploit ourselves. And the result is the attack vector in the Solidity have a really impressive result that it fully detected with no form detections. For example, the recency attack, we can detect it with 10 positive, 10 true positive, and 7 true negative detections, and there's no false detection at all. And about the result when we try to detect the overflow cases in the EVM level, that we can not detect the variable that have the size is less than 32 bytes, and there's some form positive cases that appears when the recency occurs and the overflow value is equals to the index of the written slot. And some attack vectors in the storage overreading cases EVM level, we can just cannot detect the cases that the slot is overridden by a value whose type is the same with the current slot, and there's some form positive appears when the array and the length of the array is manually set to a extremely huge value. So what we have did in this project, the ABBE tool have been tested through the step of we give out a short taxonomy of these smart contract vulnerabilities, and then we classify the smart contract attack vectors based on their on the track of each attack, and we also propose some methods to detect each kind of attack vectors, and this method can be used to detect some zero attack in the future, and the ABBE is fully built and tested and gives some good result. However, the ABBE tool still have some limitations because it can detect the attacks that having the result related to the variable type. So this is the end of our talk. So please give your hand if you have any questions. Yeah. So I have some questions here. The first question is, how scalable is ABBE current security scanners for Ethereum smart contract? The ABBE tool can run in a high scalability due to it really fast. Although it have to re-execute from the first block to the last block to retrieve all transactions that have been executed in the Ethereum network, but this just have been need to done just one time for each kind of attack, for each kind of contract. And the second question is, will ABBE be able to migrate the tokens and the smart contracts on the ETH? If so, how? I don't get these questions.
Yeah, because our tool is about how to detect attacks happen on the smart contract platforms. We do nothing with migrate the tokens or smart contracts. So yes, I think our scope of our work.
So the last question is, would ABBE be able to detect attacks by the multi-core symbolic execution framework?
I think I would rephrase this question to be, can we detect attacks that's already detected by multi-core, right? And yeah, I think you can show the last slide. There's some limitation, but yeah.
Actually, I think that there's some misunderstanding here. The multi-core symbolic execution is a framework that does the symbolic execution that to explore some path and give the result of all the explorable part of the contract, but it's not the kind of
It's auditing tool. Multi-core is auditing tool.
Yeah.
But take another approach. We try to detect
it's a different approach here. We try to detect the attack, but the multi-core is trying to play the symbolic execution in the smart contract.
But yeah, I think this question is still relevant because they want to know if you can detect the same bugs that can be found by the multi-core. So I think you can show the result limitation. So you can see that, okay, we detect similar bugs, but you have some limitation as well.
Okay. So our limitations in that we can not detect the attack that having the result related to the variable time. In other words, that if there is a result, for example, the overridden vulnerability, if there are two types, if the two variables have the same type, so we cannot detect it at all. And the last question, slightly off topic, wondering if you're aware of Stellar smart contract. Stellar has smaller instruction set than Ethereum. Does it make it less vulnerable to the attacks that you covered?
Okay, so for this question, personally, I do not do anything with Stellar smart contracts. But I think the idea is that each platform has some very unique bugs. Like some bugs happen on Ethereum, might not happen in Stellar platforms. But anyways, I probably smaller instruction set is not the reason that it can have less bugs anyway. But yeah, we don't look at the Stellar platform, so we have no idea about that.
Okay, thank you.
So no more questions? Thank you so much.
Thank you for having me.